Hello there, welcome to another tutorial. Today we are looking at a particle moving down an incline with air resistance. However, today is quadratic air resistance, which makes a big difference because with quadratic air, when you have quadratic, it will make a big impact on the way the system works. So we're going to look at this example now, and we're going to work it out. So as you can see, we have the triangle here. We have the particle here. Here's the particle. It's moving downwards. It's moving down the plane, and you can see the triangle there. We have the theta. We've done this. We've done this before with an inclined plane. We know that it's mg moving downwards, gravity, and then you've got the angle, the normal angle here, and then you've got the mg sine theta direction, which is very important, which is the same direction as acceleration. The acceleration is tangential to the plane. So it's at sine theta. The acceleration is at sine theta. That's the angle it's at sine theta. Anyway, let's look into the first how we're going to do this. So what we do is we do F equals ma, F equals ma, and to do that, what we're going to do is we're going to do, I'll write it here, mass times by acceleration. So it's a particle really, is of mass m times by the acceleration is equal to, and then we have mass times by gravity, the acceleration of gravity, times by sine of theta. So that component, because that's parallel, that's tangential. Well, yeah, parallel to the incline, the incline angle. And then we have also minus, and c. We're picking c for the constant, v squared, and that's a lot. That kind of air resistance, that kind of drag force is a lot more realistic because in reality, drag, is proportional to v squared, not v. Because in other videos we've done, we've looked at velocity as a linear term. However, in real life, in real situations, it's going to be a quadratic, and c would actually be equal to in reality would be equal to a half density of the fluid, and then the coefficient of drag, the drag coefficient, and then the area of the surface, the cross-sectional area, potentially, and then that's just c. And then when you add in v squared, like this, you get the full drag force equation. And the density is the density of the fluid. However, that's not needed in this. We don't need to go into that level of detail for it. If you do engineering or if you do fluid dynamics at any point, you'll see it in physics as well. Any kind of fluid dynamics, you'll encounter that equation. And I will be open to doing fluid dynamics videos if you're interested. Anyway, with that, what we want to do now, we want to rearrange it into a better form. So let's start by dividing everything by m. So you can see the equation there. Let's divide everything by m. So with that, you're going to get it into this form here. Acceleration is equal to g sine of theta minus c over m v squared, like that format there. And now what we want to do is we want to basically write it into this format here, dv by dt, as acceleration is equal to dv by dt. It's equal to the derivative of velocity with time, is equal to, and again, g sine of theta minus c over the mass velocity squared. Now that form there is important because now we're looking at a differential equation and we want to solve for v. So when you're doing these kind of differential equations, you want to basically separate the variable. That's the type we want to look at. So what we can write it as is we can times everything by dt, and when we get that, we're going to get dv is equal to g sine of theta minus c over m v squared, put it all in brackets like that, times by dt. So you see now we have it in this form now. We are ready now for the next step, which is integration. If you haven't covered integration, I recommend you look at integration first before doing this. Integration and calculus and differential equations will come up a lot in any kind of dynamics or mechanics, especially dynamics, because you're looking at changing things with time. Anything that's changing with time, any kind of physical thing like that, is going to have a lot of this kind of stuff, a lot of calculus in it. So anyway, what we want to do, we're going to divide both sides by this, by g sine theta minus c over mv squared. Divide both sides by that, and you end up with dv by g sine of theta minus c over mv squared. It's not great that, I apologise. The thing is, the common method here is to use, I'll tell you after, once we get here, but we are going to do it, we're going to go a little bit different from the common method here. Is equal to, and then dt. So you've separated the variables now, which is, this is a, you know, when it comes to differential equations, this is separating the variables type. And you can see we've separated them, so we've divided everything by g sine theta minus c over mv squared. And now I've got it into a form where we can actually integrate. So let us go below that. Let us go there and let's set up the integral. So what we're looking at now, to set up the integral, what we're looking at basically is the integral between, and we're going to say it starts at rest. We'll say the particle starts at rest, so we can put 0, and then the current velocity. Because you can use v0. You could write v0 there, but in this example, we're going to just say it starts from rest. We're looking at a function. We're looking at the function as if it starts from rest. But if you want to assume it has an initial velocity, then you just put v0 here. But we're going to assume it starts from rest in this example. We're going to derive a formula for starting from rest. Anyway, and it's going to be 1 over g sine of theta minus c over v squared. Let me just write it more clearly. Well, yep, dv is equal to the integral between 0 and t, like that, dt. So now I've got this integration to do now. The thing is, this would, when you look at v squared like that, v squared, a lot, you would often assume that you'd have to do the hyperbolic function method of integration, but you don't actually have to do that method. That method might make it easier, but in this example, we're not going to do that. We're going to actually do it by using. I mean, look, there's a very important identity in a lot of maths. If you've seen this, you might you've probably seen this. We know that a squared minus b squared, just assuming, we're not saying that's acceleration, we're just saying a random letter, a random a, a random b, is equal to a plus b, a minus b. Now this is very important because this can, if you do this, you can turn it into partial fractions potentially, and with that we can make it a lot easier to integrate. So we know that identity, in maths. Now, right now it's quite messy. We don't want to have, it's quite a messy format. We don't want to have it in that form to do that with. Otherwise, you're going to have a lot of square roots. It's going to be, of all these complicated variables. It's getting very messy. So what we're going to do, we're going to divide everything by sine of theta, g sine of theta, on that side. Only on that side. Only on this side. Only on this side here. We're going to divide everything by g sine theta. So when you do that, you're going to end up with basically the integral between 0 and v, 1 over g sine of theta, and then over 1 minus c over mg, let me check, sine of theta, v squared. So you get into that. We're just looking at the left hand side at the minute. So you get into that format. Now with this, we can just move this 1 over sine theta to the outside of the integral here. So what we can do basically, let me draw that out. I don't want to keep that on here. It won't be clear. So we can move it to the outside of the integral. So what we can do, we can get it into this format here. I'll show you the final format we can get it into before integrating. 1 over g sine of theta, like that. And then the integral between 0 and v. And then what we're looking to do is it's going to be 1 divided by, that's way too much space, isn't it? We don't want to have that much space between the 1 and the division part. But yeah, divided by, and then it's going to be, again, 1 minus c over mg sine of theta v squared, like that, is equal to, sorry, not that, sorry, dv is equal to the integral between 0 and t of dt. So yeah, there we've got the final form there, the format there. That's a good format. We've got it in there. Wait until that loads and then you can see it. So yeah, you can see it's the now we can see this format here, and you can see the one. Sorry, you got 1 over sine g outside, and this is important now. Now this to work with will be annoying. So what we're going to do, we're going to make a simplification. We're going to pick a random letter b squared. We're going to say is equal to c over mg sine of theta. This is going to keep things simpler. So with that, we can then rewrite the equation again. We'll write it over here as 1 over g sine of theta, and then the integral between 0 and velocity, the current velocity, and then it's going to be 1 over 1 minus b squared v squared dv is equal to the integral between 0 and t dt. So we've got it in this format now. Now this looks like something we can actually work with now. And at the end, of course, we can put the b squared back in. What we're going to do now, we're going to go to the next part and we're going to actually solve this. So this is now the next part is this question. What we're going to do now, we're going to try and solve this. So if we look at it now, let's write this out first. 1 over 1 minus b squared v squared. What is that equal to? Well, we're going to do partial fractions. A over 1 plus b velocity plus b over 1 minus b velocity. So you have these partial fractions here, because we know it can be in that form as it's b squared v squared, which is basically, obviously b squared v squared is equal to bv squared, and then we know 1 is equal to 1 squared. So therefore we know it's going to work in terms of that formula we looked at, where it was a squared minus b squared. It's the same thing. You can see it's the a squared, and then minus b squared. You can see it's the same thing. So with that, what we're going to do, we're going to times everything by, we're going to first of all put it in the right format. So that should actually be 1, I'll put it over here actually. That can be rewritten as, I did jump a step there. That can be written as, 1 over 1 plus bv, 1 minus bv is equal to a over 1 plus bv plus b, it's not very clear, b, I apologise, over b, that. So we've got it in this format. We're going to times everything by this part here to expand it out. So, and when you do that, when you times everything by that, you can do it yourself, but that's going to end up converting into 1 is equal to a times by 1 minus bv add b times by 1 plus bv, like that. The reason why is when you times everything by 1 plus 1, by that, the 1 plus bv is going to cancel, and it's going to be a times by 1 minus bv, and the 1 minus bv is going to cancel, and it's going to be, b times by 1 plus bv. So that's going to cancel, and you're going to get into this format here, which is an equation to solve. Expand it out, you're going to get 1 is equal to a minus bva plus b plus bvb. And to solve this, what we want to do, we know when we look at this that a plus b is going to equal to 1, And it's you basically, the way of looking at it is you want to look at it like this. So I'll show you how I look at it. You see it there like that. The way of looking at it basically is to, let me just write it here actually. It's like this 1 plus 0bv. That's how you imagine it. Is equal to. If you haven't done partial fractions, I would recommend looking them up as well. They're really important for integration. It's a really useful thing to know in terms of in integration. So I would definitely recommend looking it up. A plus, we can collect them together. A plus B. And then plus it's B minus A, yep. B minus A B V. So you've collected the terms now. So you've got it in that format now. So what we want to do is we want to basically, so now we've got it in that format, what we want to do is we want to go to over here. We know 1 is equal to A plus B, and we know therefore that 0 is equal to B minus A. So therefore A equals B. And therefore we can substitute in, so 1 is equal to A plus A. 1 equals 2A, and therefore A equals 1/2. Okay, so now we have that, we can now get into a final format of, we can rewrite the whole thing as 1 over g sine of theta, the integral between 0 and velocity, and then 1 over, should be a half, times by, because they're both equal to a half, times by 1 over 1 plus bv plus 1 over 1 minus bv. We know this to be true. dv, and we know the integral between 0 and t, like this integral between 0 and t, dt, is integral of 1. So, and we know the integral of 1 is just going to be t between 0 and t, so that converts into, it's just going to basically be t like this between 0 and t, and that's just equal to t. Anyway, I'm going to get into a better format to work with it. Okay. 1 over 2g sine of theta, integral between 0 and v, 1 over 1 plus b v. I've just taken the half outside, as you can see, plus 1 over 1 minus b v, and that's all like this. It's not very clear, I apologise. dv is equal to t. To integrate that, that's just logarithms. We know that, the integral of between 0 and v of ln of 1 plus, I've already done the integral there, of 1 over 1 plus bv. Well, that's just a natural logarithm integral. If you haven't done that, we know that's going to therefore be, I'll show you what the integral that is. If you've done integrals, you'll know that's equivalent to ln of 1 plus bv. And then with the chain rule, since you times by bv when differentiating, it's just going to be 1 over b for that. And it's going to be that because it's basically that between 0 and v. It's that between 0 and v, which is just going to be equal to 1 over b ln of 1 plus bv. And then the other one is exactly the same. The only difference that is a negative sign, the integral between 0 and v of 1 over 1 minus bv dv is going to equal negative 1 over b ln of 1 minus bv due to the negative sign. If you times it out now, you'll see negative b times by negative 1 over b is 1. So the final format therefore 1 second. Yeah, so the final format is going to be 1 over 2g sine of theta, and then in the brackets ln of 1 plus bv minus ln of 1 minus bv, like that, is equal to t. And with that, we can times everything by 2g sine theta. You know, we can times everything by this part, which you're going to end up with basically. And you can, you can times by the b as well. See, the b on the outside as well. So there should be a b as well, sorry. It should be a b on the outside as well, like that. Times everything by that as well, and you're going to end up with ln of 1 plus bv minus ln of 1 minus bv, like that, is equal to 2g bt sine of theta. Okay? And now logarithm rules. We now need to use logarithm rules. You know, if you know, into the logarithm rules, we know that ln of 1 plus bv minus ln of 1 minus bv is identical to ln of 1 plus bv over 1 minus bv, like that. So then, therefore, this is going to be equal to, and with logarithms, you do to the power. Sorry, not yet. Sorry, it's 2g bt sine of theta. And of course, with logarithms, we can rewrite it as 1 plus bv over 1 minus bv is equal to e to the power of 2g bt sine of theta, like this. I would recommend you look up logarithms if you haven't done it. And we can expand that out into 1 plus bv is equal to, let me double check, 1 minus bv, like this, e to the power of 2g bt sine of theta. And now with that, we can rearrange you can very simply rearrange it into this format. bv plus b, that's not very clear, I apologise. You can very easily rearrange it, plus bv e to the power of 2g bt sine of theta is equal to e to the power of 2g bt sine of theta minus 1, like that. And then what we can do, a very simple step we can do now, is simply take out a factor of bv, like this. 1 plus e to the power, we'll call it the e to the power of a to simplify it, as it's overcomplicated right now, equals e to the power of a minus 1. And therefore, v is equal to e to the power, because yeah, a is just that, is just 2gt, a is just that. It's just to simplify the process. The power of a minus 1 over e to the power of a plus 1 times by b, like this. And now, if we substitute in b and a, so both of them, remember b squared is equal to 2g, sorry, it's equal to c over mg sine theta. So all we have to do is subject. You put it in, and we get therefore a final result of a velocity as a function of time is equal to e to the power of 2g bt sine of theta minus 1, like that, and then over, a bit further, over, and then b, remember, is going to be the square root, so it's going to be this, therefore b is going to be c over mg sine of theta, the square root, like that. It's getting quite algebraic now, but it's all right. And then e to the power of 2g bt sine of theta minus 1. And yeah, that's the final form you get it into. That is the final equation. That's the final form for this. And that is, you know, a particle sliding down an inclined plane, a smooth one, with quadratic air resistance, you know, quadratic drag. And it does get fairly complicated, but it's very, you know, it's very rewarding, the final result you get. And you see, you don't have to use hyperbolic function to do it. But yeah, thank you, and subscribe. Thanks.